Hi guys, welcome to my channel. So today we are going to begin a new series of lessons which are going to cover the calculus course, as it is mostly given to first year students. You see, so this is going to serve as the first lesson, which is going to cover some preliminary work that we are going to need in our study of calculus. You see that? So in today's session, we are going to talk about set theory, which is just simply the study of sets. This video, I'm going to split it into two parts. This video is going to be the first part of our study of set theory, which is going to cover the following objectives. So the first thing that we would like to talk about is the definition of a set. And then we're also going to introduce some notation that we're going to need as part of the discussion. And then after that, we are going to look at different ways of how we can represent set. And then finally, we are going to talk about subsets, you see. So that's what is going to be covered in this video. And I hope it's going to be a useful introduction for any student, whether you're going to be leaning towards some algebra course or some calculus course. You definitely have to start by first having a good background on set theory. Then we can now move on to other areas of all these subjects. Okay, so first thing first, now we are going to move on our discussion. And the first thing that we're going to begin with is to actually start talking about sets. So now let's talk about definition. Sets. What is a set? You see that? So there are many ways in which different authors actually define sets, and I'm gonna stick to one of the definitions that is quite common in many of the books that you can read on this subject. And what we call sets are defined as follows. So a set is a well-defined collection of objects. You see that? So a set is a well-defined collection of objects. This is the definition that we can usually get in most of the books that deal with this subject, that it is a well-defined collection of objects. But what does it mean now to say it is a well-defined collection? You see that? So well-defined is a line which simply tells that the way the set is described to us, it will be easy to tell what are the objects that are contained within that particular set. You see that? So it simply means that it is easy to tell what objects are in the sets. You see, so that's what a set really is. A set is just simply a well-defined collection of objects, which means you can picture a set as some sort of an environment within which there are some objects that are placed in that particular environment. You see that? And there is a way of describing that set in such a way that everyone, by just studying the description, they can be able to discern what exactly are the objects that make up that particular set. You see? So that's what a set really is by definition. But then the other thing that you have to know is that the objects that make up a set are usually referred to as the elements of that set. You see that? So the objects remember I said one thing that characterizes it is something that has to have the presence of objects within it. So the objects or the individual objects that are contained within a particular set, we refer to those as elements of that set. You see that? So the correct name that we use for the objects that are found within a particular set, we refer to them as elements, or some books they say members. But the common term that you're going to be coming across quite often is elements of a set. So whatever is found within a set, we call that the element of that particular set. You see? So that's what exactly a set really is. So it will be a good thing for you to have a good understanding of this definition so that you may be able to understand things which are sets and things which are not sets, you see, as you go into your studies. Okay, so what next? You see. So, when we talk about sets, we usually name them using uppercase letters such as A, B, C, etc. like that. You see. So one thing that you have to know, most of the time when in mathematics you are dealing with particular objects, we always want to have names that you can use to refer to them every time when we want to make use of them. You see that? So a set, since now we are leaning towards studying sets under mathematics, it means these things actually we want them to be mathematical objects, which can be used to perform some mathematical operations. You see that? So for them to be mathematical objects, we have to find a nice suitable way of representing them. You see that? So that then we can now deal with them using our mathematical operations that we define on them. You see that? So since you have seen that a set now is comprised of two things, it is composed of a boundary, which is such that within that boundary there are objects on the inside. You see that? So the thing that contains, that holds all the objects of a set, we refer to that as the set itself. So when we want to talk about that thing, we have to find a suitable way. So one of the ways in which we use to represent set is by making use of the uppercase letters of the alphabet, which is A, B, C, or sometimes suitable Greek symbols. So it is not only the letters of the alphabet that I use for giving names to sets, but we can also use even suitable Greek symbols. You see that? So, most of the time, let's say maybe I want to talk about a set which consists of numbers that are even numbers. You see that? So we can choose maybe a Greek letter which almost has the symbol E, like this one, that is used mostly in many currencies outside there. But most of the time, every time when we want to name a particular set, we want the name to be so suitable in such a way that the name itself is connected in some way to the original or the intrinsic nature of the set itself. You see. So it will be good for you to be aware of these things when you are to study a subject like set theory. You see that? Then the other thing that you should also know is this one. You see that? So the members or the elements in a set are usually represented by small case letters such as A, B, C, D, 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 or even names like actual names of objects. So when it comes to the elements of a set, or you can use the numbers 1, 2, 3, 4 as well. You see that? So one thing that you should know is that there are times where we don't want to talk about the set itself as well, but we want to refer to a particular object that is contained within a set. So objects in a set, most of the time when it comes to representing them, we always choose to use the lowercase letters of the alphabet like A, B, and C. Or sometimes when that cannot be done, you can actually refer to them using their actual names. When it's a set of animals, you will just state the name. It's a tiger, cat, and whatever that are contained within that set. Or sometimes you can just prefer to use numbers to refer to the elements that reside within a particular set. You see. So these are all the basic fundamentals that you have to know if you are to start working efficiently with sets. To always know the convention that always reserve uppercase letters to denote the set, and small case letters to denote the things that reside within a set or the elements of a particular set. You see. So those are the things that you should know most of the time. Then the next thing that we want to talk about in sets now is basic notation. You see, so since this is a mathematical subject, we want to make sure that it's a subject that uses as much mathematical symbols as possible. So we try to make sure that some statements that are quite common in this subject, they are represented using particular mathematical symbols, so that at least the communication is very short and simple, as we would need as mathematicians. You see that? So now we are going to talk about some basic notation that we are going to be quite frequently using, mostly as far as this course is concerned. You see. So what is that notation? So the first notation that we're going to discuss is the E, the symbol E in set theory. So there is this small symbol E, which stands for is an element of. You see that? So there is this symbol, small letter E, which stands for is an element of. You see that? So which means that if A is a member of a set A, we usually write A is an element of A, like that. You see. So this is how you will get to use this notation. You see. So there is this small letter E, which is almost like the epsilon, but it's not exactly the epsilon. We can just say the curl E, which is also a lowercase letter. So it is used every time when you want to communicate an idea that a particular element belongs to a particular set. You see that? So if 2 is a member of if 2 is a member of the even numbers, then you write 2 is an element of curl E, where curl E stands for the even numbers. That's how it works. You see that? But if A is not a member or an element of the set A, then we write A is not an element of A, where now we use the same E, but now with a slash on top of it. You see that? So every time when you see an E with a slash on top of it, it means now it's talking about the negation of the original symbol. You see that? So when E stands for is an element of, then E with a slash on it, it stands for is not an element of. You see, so that's what this notation stands for that sits here. You see, so this is the basic notation. We are still going to see as many notation that we are going to be coming across as we discuss this whole subject, like that. You see, but it's good for now to at least have this basic notation in place, because it is what we're going to need for most of this discussion of set theory. You see that? Okay, now that you have familiarized yourself with one of the basic notations of set theory, the next thing that we want to talk about is the representation of sets themselves. You see that? So these objects that we refer to as sets in mathematics, there are many various ways in which we can represent them. You see that? So the common ways or techniques that can be used to represent sets, they are as follows. So we have one which is called the brace method. The brace method is a method which uses what we call the braces. So the braces, it just means just curly brackets. You see that? So braces, they are just simple curly brackets. In another way, that's how you can actually name them. Then also, another way of representing sets is by the use of what we call Venn diagrams. You see, so these are some of the common ways in which we can use to represent these objects that we call sets in mathematics. We can use what is called the brace method or the Venn diagram. And both these two representation techniques, they are quite common in a much similar way. So we can't say that this is the most common than the other. So it's just that there's some problem where it's much more simple to work with Venn diagrams than it is to work with braces. But there are some situations whereby braces, they're just sufficient and they make life easier to just represent sets and move on and discuss whatever we want to discuss, you see. So now what we're going to do next now is to try and understand how these two representation procedures work in representing sets. So what we're going to do now, we'll first start by looking at the brace method. So how do we use braces to represent sets? You see that? So when it comes to braces, there are two ways in which sets can be represented using braces. You see that? So there are two different ways in which sets can be represented using braces. And the first way in which sets can be represented using braces, it is actually to write down inside the braces each and every member of that particular set. You see that? So like, for example, let's say we are talking about the set, the mathematical set that consists those drawing instrument. Let's say now I want to represent it as a mathematical object. In this case, how am I going to do that? So how am I going to do that is I'm going to open a brace and then I'm going to list all the individual things that form that particular set. So I'm going to say there's that 15 centimeter ruler. So I'll write 15 centimeter ruler. And then again, I'll look that inside there is a protractor. So I write down that there is a protractor, then there is a divider, then there is a compass, then there is a 30-60 set square, then there is a 45 degree set square, then I close my braces. You see that? So this is one way of actually representing sets. Yeah, you can just open a brace, list all the members in that particular that make up the set, and then you close the brace. You see, so this is one nice way. But definitely, if you can start looking into sets a bit more detail, you will see that actually this is something that cannot always work. It can be the best procedure to use when you are dealing with finite sets in which also the elements that make up that set is just a small number. But if we have a huge number of elements within a particular set, it becomes a problem. But there are some other instances whereby it's easy even to represent even sets that are infinite in number. Like, for example, let's say maybe you want to list all the sets of even numbers. So if you want to list all the set of even numbers, you can just list a few, 2, 4, 6, then ... You see that? So the 3 dot notation, it is a notation that is used in times whereby it's easy to continue the set from where it ended up to an infinite number of terms. You see, so like for example, now if someone sees 2, 4, 6, they can easily know what is going to come after the 6 and what is going to come even after that number and what is even to come next, things like that. So this is how braces can be used most of the time. You see that? So this is how the brace method work. But these two examples that I've so far given, they are actually showing the same representation. So there is a third way of representing sets using braces, which uses what is called a condition. You see that? So sometimes the members of a set or members that belong to a particular set, they can happen to satisfy a particular condition. You see that? So if we are aware of whatever the condition is that is satisfied by the members of that particular set, then we can easily state maybe one of those members. Like I can now say, let my set be made up of member n, such that, so these two dots, they mean such that in mathematics, especially when they are used in set theory. So they mean such that n maybe is an integer with n like with n divisible by 2. You see that? So this is a nice way. So actually, if you can look at the sets 2 and 3, one might actually think that these two sets they're actually different, but they're actually the same set. You see that? Especially when I consider only positive integers. You see that? So if I consider n to be every positive integer which is divisible by 2, then you will actually see at the end of the day that this set that I have here and this set here, they are just equivalent sets. But this now example serves as a demonstration that there are always many ways to represent sets. We can see now that in part number 3, we have used braces to represent the set, but instead of listing all the individual members that make up that particular set, we have just listed a representative, and we have listed also inside that same bracket a definition or a condition that is met by n. So we can see that n is not just anything, but it is something which is divisible by 2, which means n is anything that 2 can divide. So which means it can be 2, it can be 4, it can be 6, or it can be anything, which shows us that actually these two sets are just one and the same thing. You see, so this is the reason why you have to familiarize yourself with the use of braces to represent sets, and also how to represent sets using these specifying conditions like what we have just done here. You see that? So one advantage that the braces have, so advantages of braces are that they can represent both finite sets and infinite sets. So that's one advantage that these braces has over all the other representation that we have so far. So you will find that this is obviously one of the most preferred technique of representing sets, because it can cater for any different type of set, whether it's a finite set, whether it's an infinite set. You see that? So a finite set is one in which the number of elements that make up that particular set has a limit. You see that? There is an end point to say it goes to this end. Whilst an infinite set is a set which is such that the number of things that reside within that particular set is infinite, meaning there is no particular limit to say this is where the set ends. It just continues throughout. You see that? There is no end point. There is a starting point, but there is no end point most of the time. You see? So this is how exactly we use braces. Then let's now move on to talk about Venn diagrams. So what are Venn diagrams? So Venn diagrams, they are just shapes. You see that? So Venn diagrams, they are just shapes. It's just that most of the time, the shapes that we use, most preferably, we can either use circles or squares to represent sets. You see, so a Venn diagram just simply means a shape. So now, how it works in representing sets is that this shape has a particular name, which actually is a description of the set. Then on the inside of this shape, we always list the members randomly that make up a set. So like maybe let's say we want to represent even numbers from 2 to 10. So you will list them inside 2, 4, 6, 8, 10. So it doesn't matter how you list them on the inside. They just all have to be there within that particular set. You see that? So even here, if I want to list, maybe it's a set of different sports that are done by different people. So I'll write down all the different names of the sports that are done by different individuals. So this is how Venn diagram work most of the time. You see that? So it's just using shapes to represent sets in such a way that within these sets, we just list all the elements that make up that particular set. You see that? But one thing that you should pay attention to now is that Venn diagrams can only work efficiently to represent sets that are reasonable, finite. You see that? So Venn diagrams, they can work efficiently when you are representing a set which is reasonable, finite. What I mean by that is like, let's say I say you want to represent a set which consists of numbers 1 to 100. Yes, it's a finite set, but still this is a very huge set to list all its individuals. So something like that, you can use only braces to if you are to represent that. But here we just look at the size of the set that we are dealing with. So if it is a reasonable finite size, in such a way that you can list all the elements within it without taking much time to do that, then that's where we can come to use Venn diagrams to represent these sets like that. You see. So these are all the different ways that we have available for representing sets in mathematics. You see. Then the last thing that we want to talk about for now is subsets. You see that? So it is sometimes possible to extract one set from another set. You see that? So in mathematics, most of the time, sets that we use to do some mathematics with, they always come somewhere. You see that? We always picture the existence of a space which is such that everything or every set that you deal with seems to be coming from there. You see that? So sometimes we can even form new sets just by using those ones that we have. You see that? So I can have a set A in front of me from which I create another set just by taking a few individuals from that particular set and manufacture a new set. You see that? So a set which is obtained from another set is called a subset of that set. You see that? So one of the things that you should know is that it is a set which is manufactured from another set. We call that a subset of that set. You see that? So if a set B or if a set A is obtained from B, then we say A is a subset of B, and we write A is a subset of B, or A is a subset of B. So there are two notations that can be used to say A is a subset of B. You can see that there is this, it looks like a C, but it's not actually a C, but you can take it as some sort of a Greek C maybe. So you see that there is a C which is just a C and a C which is a bar at the bottom. So these two things, they can all be used to refer or to mean that one set is a subset of another, but they have slight differences between them. So let's talk about those differences that are there between these two symbols that we have just introduced there. So now let's look at difference between this and that. So what are the differences between this and that? You see, so this means that A is a subset of B, which is possible equal to B. You see that? So every time when we use this notation that has a bar at the top, it means there is a possibility that these two sets can actually be equivalent to each other. You see that? So when there's a possibility that A is a subset of B, then you should always know that when we use this particular notation, then you should always know that there is a chance that actually A can be just the same set B without having any changes. You see that? So, but when we use this notation now, when we say A is a subset of B like this, means A is a proper subset of which can never equal to B. You see that? So that's what this notation stands for. So when we remove the bar, it means A is never going to be equal to B. So a subset of a set which can never be equal to the original set, we call that a proper subset. So whenever we use this notation, it means we are saying A is a proper subset of B, which can never be equal to B in any way. You see? So that's the distinction that you have between these two different types of notation that we have just stated there. You see? So it's a good thing to make sure that you have quite a good understanding of everything that we are seeing here. You see that? So that's one of the basic things that you must make sure that you know pretty well. Then now, there are some certain results that you have to know concerning subsets, which I will call some basic theorems. So as someone who is doing first year, you might be asking yourself, what exactly is a theorem? A theorem is a statement in mathematics that we know to be true, in which there is proof that is actually true. You see that? So every time when we know about the truth of a particular statement and there is proof that it is indeed a truth statement, then we usually refer to those statements as theorems. You see that? But now you don't have to bother yourself much about an understanding of all this. In second year, that's where everything is going to be made clear. But for now, just know and be aware that theorems are things that are going to be quite more often in your study of math, and you should just get used to them. So there are just some basic theorems that I want to state for you right now that are connected to subsets. You see that? So, but before I state these theorems, there is something that I must mention. See that. So, it is possible. It is possible to have a set that has no elements in it. So, so far, if you have seen, we've always described it as a set as a collection of objects. But when we have something which or a region in which there is nothing in it, we actually treat those things as set again, which we refer to as sets with nothing. So a set which has nothing in it, there is a special name that we use to call it. So a set with no elements is called an empty set. You see that? So every time when we have a set with no elements in it, we refer to that as an empty set, and we represent it using so the symbol for an empty set is a 0 with a slash on top of it. So if you want to refer to a particular set as being empty, that's the symbol that we use. We say 0 with a slash, meaning it's an empty set inside it. You see? So yeah, it's good to be aware of this particular set, because the theorems that I want to state, one of it has something to do with that, and it goes as follows. So the first theorem that I want to tell you is that the empty set is a subset of any set. You see that? So one thing that you should know is that the empty set is a subset of any set, because if you try and study the definition of what it means to be a subset, then you will actually come to realize that yes, indeed, an empty set is actually a subset of any set. Then two, the other thing that you should know is that the set itself is a subset of itself. You see that? So a set itself is a subset of itself. You see that? Because subsets are built by extracting things from another particular set. So let's say now I take everything that is inside. It means I manufacture that original set that I had before. You see? So this is how everything goes. Otherwise, for now, we'll cut the first part of this lesson at this point, and then we are going to continue a part 2 session, which is going to come after this one, in which we are going to now look at some operations that one can do with these objects that we have introduced. Otherwise, thanks for watching, guys. Meet you in the next video. Bye.